This image helps us look at how the displacement of this simple pendulum, which is undergoing simple motion, varies with time. The ground is moving at constant speed, so this axis here is basically time. Okay, and this axis here is displacement. So you can see you're getting a sinusoidal graph here, either sine, a cosine, and so on. Here we have a pendulum which is displaced in the positive direction and then released. Plot a displacement time graph, velocity time graph, and acceleration time graph. Okay, firstly, this is displaced in the positive direction like is shown in the graph, and it's released. So that means it starts from rest. Okay, then it's going to go towards the equilibrium first. So we know it's going to start with a positive displacement, and it's going to go towards equilibrium like this. Okay, and then it's going to overshoot because it's got momentum. It's going to go beyond the equilibrium and it's going to go into negative direction. Okay, it's going to end up there, so it becomes negative. At which point it will stop at the very end and it'll turn around and it'll go back towards the equilibrium, and then it'll go beyond the equilibrium toward the positive direction again, and then this will just repeat. Now for the velocity time graph. So we're releasing this pendulum from rest, so the initial velocity should equal 0. So I'm going to put a cross there at t equals 0, velocity equals 0. And I can check this on the displacement time graph as well, because the gradient of a displacement time graph equals velocity. So the steepness at t equals 0 should equal 0. Okay, then as it gets pulled towards the equilibrium, it's going to go through the equilibrium, but when it's going there, it's going to be going in the negative direction, so you can get a maximum speed going in the negative direction. And let's check this on our displacement time graph by drawing a gradient there, and you can see getting a steep gradient, but it's negative. Okay, and then it's going to go all the way to the left hand side where it's going to stop. Okay, so the velocity will equal 0 again on the maximum negative maximum displacement. Okay, and then you can check that again using gradient here. It's flat. There's a turning point, so it's going to give you a 0 gradient there. All the turning points will give you 0 velocity. Okay, then now let's try to predict using the gradient of the displacement graph. So if I draw a gradient here, you can see there's a maximum positive gradient there. So it's going to give me a maximum velocity positive. Okay, and then again is gradient at the other end. It's a turning point, so it's 0. So we can just complete this graph by just joining them with a sinusoidal curve like this. Okay, let's look at the relationship between the displacement and velocity time graph. You can see the velocity time graph is obtained by shifting the displacement time graph backwards towards the left by 90 degrees. So the phase relationship is the velocity is pi over 2 or 90 degrees behind the displacement time graph. Now for the acceleration time graph. When the pendulum is displaced in the positive direction, there's going to be a restoring force pulling it back in the negative direction towards equilibrium. So the acceleration is going to be negative at the start. We can check this on the velocity time graph because the gradient of velocity time graph is equal to acceleration. So if I drew a mini tangent at t equals 0, I should get a negative gradient there. Okay, and then as it goes through equilibrium, well, at the equilibrium, there should be no acceleration. You can check this on the graph. There is 0 gradient. There's a turning point. And then as it goes beyond the equilibrium, it's going to have into the negative displacement. Now it's going to have a positive acceleration, pulling it back in the positive direction there. And you check this using the gradient. And if you repeat this process, you get a shape which looks like this. And then you can connect them using a curved sinusoidal graph. Okay, so you can see the relationship between velocity and acceleration is similar to displacement and velocity. The acceleration is pi over 2 or 90 degrees behind velocity. Okay, what's more interesting is the relationship between displacement time graph and acceleration time graph. You can see they're 180 out of phase or pi out of phase or in antiphase. Okay, the reason for this is of the definition of simple motion. According to the definition of simple motion, the force is directly proportional to x but negative in the opposite direction. And force is of course proportional to acceleration, so this is what we expect. So the acceleration time graph is always going to be a flipped over version of the displacement time graph. They might not have the same magnitude, but they'll have this constant phase relationship of 180 out of phase. Okay, here we have a mass on a spring. The mass is placed on the spring and allowed to come to rest first, and at t equals 0, the mass is given an upward impulse. Plot a displacement graph, velocity time graph, and acceleration time graph. Okay, this is still simple motion. The only difference is it's a mass on a spring, but that doesn't make a difference at all to the shape of the graphs. But what is different is the initial condition, because in the pendulum before, we gave it a positive displacement and we released it from rest. But now, this is starting from equilibrium, so no displacement, and is being pushed upwards, so it's been given an initial positive velocity. So we're going to start at t equals 0, 0 displacement, but it's going to go in the positive direction, so it's going to going upwards. Okay, there it will stop and it'll come back down, and then once it's gone down, it will overshoot and it'll go below. It'll go below the equilibrium, go into the negative direction, and then come back to the equilibrium, and so on. Okay, now for the velocity time graph. If you remember, we gave an initial upward velocity, so it's going to start with a positive velocity like this. Okay, the relation between displacement time graph and velocity time graph is the gradient. So if we look at the gradient, you should get a positive value there. So I'm just going to use gradients for the rest of it to just complete the shape. So that's a 0 gradient there. Okay, so it goes through 0, and then you get a negative gradient there. So it's a negative maximum velocity, 0, and so on. Okay, so you can use this to plot the graph, and you're getting, in this case, a cosine graph like this. Can you complete that? And because the relation between them is the same as before, between the displacement and velocity time graph, it's pi over 2, 90 degrees out of phase. Okay, for the acceleration time graph, so it starts off at the equilibrium where we gave it a positive velocity. Because it was at the equilibrium, there was no force on it. Okay, it hadn't been displaced at the very beginning. So the initial acceleration is 0. And you can check this using the gradient of the velocity time graph because that's equal to acceleration. So the very start, gradient is 0. Then I'm going to use the gradient for the rest of it. So the gradient there is negative. So you get negative acceleration directly below it. Okay, and then 0 gradient. So 0 acceleration, positive gradient. So positive acceleration, and then 0. So you get a negative sine graph in this case. Okay, so what's the relationship between this velocity time graph and acceleration is pi over 2 again. But again, what's more interesting is the relationship between displacement and acceleration. It's 180 or pi because of the definition of simple motion, that acceleration is in the opposite direction to the displacement and direct proportional. It doesn't really matter what the initial condition is. The relationship between the graphs is the same. So when you're going from a displacement time graph to a velocity time graph, what you're doing is you're finding the gradient. Or in maths, you might have learned this as differentiating. And when you differentiate a sine graph or a cosine graph, you move it backwards by 90 degrees. So that's a quick shortcut you can use to figure out the shape of the graph. So if I move the displacement time graph towards the left by 90 degrees, I end up with a minus sine graph. You can apply this when you're going from velocity to acceleration time graph as well, because you're finding the gradient of the velocity time graph to get the acceleration, or differentiating it, so you move it backwards by 90 degrees and you end up with a minus cosine graph. The graph shows how the velocity of a 10-kilogram buoy varies with time. So it's bobbing up and down like this, and we need to calculate the frequency of the oscillation of the buoy. Okay, so in this graph, you've got some information. I recommend finding the time period, and you can find time period by measuring over as many time oscillations as possible. So in this case, 2 complete oscillations are 4 seconds, so the time period is 2 seconds. So using 1 over time period to get the frequency, we put that in, you get 0.5 Hertz. Okay, now we're asked to calculate the maximum kinetic energy of the buoy. So it's maximum when it's going through the equilibrium, and we can find it using the equation half mv squared. We've got the mass. Where do we get the maximum velocity from? Well, the graph is a velocity time graph, so you just find the maximum by reading the amplitude. So the maximum speed is 0.8. Okay, so if we put that into the equation, half times mass times 0.8 squared, you get 3.2 joules.